Hey everybody, how you doing today? Happy Wednesday. Kitties don't want to say hi right now. Alrighty. Whew. Right. Today is week 9. Holy cow. We are cruising our way through here. And we're going to talk about the list ADT this week. Again, we kind of a little bit backed up. I wanted to talk about the priority queue last week. So we got a little bit to cover with the list ADT, and then iterators and the sorted list from the interludes, and any questions you folks have about Project 4 as well, and then a little bit of midterm review. It is also my anniversary. Been married 14 years today, which is pretty cool. So I'm going to try and make it short and sweet if we can help it. if that's all right with you folks. All right, let's see. What's going on? Oh, here we go. Thank you so much, Ray. Appreciate it. All right. So what do you want to do first? Do you want to do midterm review first, or list ADT first, or project 4 questions? What sounds good to you folks? I can do them in any order. It's no big deal. Yeah, any order? Any preference? List ADT review project 4. I like it, Dusty. All right, you voted first, so... Oh, someone said midterm review. We need a tiebreaker now. Which is going to come first, the list ADT or the midterm review first? Somebody else has got to vote, otherwise we're tied 1-1. Okay, that's 2 for list ADT, 1 for midterm review. So we'll do list ADT first, we'll do midterm review, and then we'll talk about project 4. I like it. All right, so let me fire up NetBeans here. Now, we've worked a lot with lists already, actually. We're using the Arraylist. So Arraylist, as you might imagine from the name of it, is backed by array-based storage. So similar to when we did the array bag, you have this oversized amount of array storage, and you're going to double each time you need to increase the amount of space. Right? Because you want to make sure you get the geometric doubling so that your average time performance, that when you do need to double, it's still on average a constant time operation. Right? So we're not going to spend a whole lot of time on, let me close that one down, on the array-based list. But we're going to spend a lot of time on the linked-based list, because that's a really fun one, and that's really interesting to talk about. So we're going to do 2353 for lists. So again, the abstract data type piece of it here is how we interact with it. Right? At an abstract data type level, I'm going to close all the other ones. We look at how do we interact with a list. And remember, a list in difference to a bag is that the order matters. So if I want to put something in, it's going to go at a particular index, a particular location in that list, and it's going to stay at that location in the list. Now, at least it will stay in the particular order. So as we go and add things and remove things, things will shift. We start up a new whiteboard here. So again, imagine a list here, right? And we got a bunch of spaces for things. So just throw out some numbers for me. We'll add a couple to our list here. So we're oversized, right? And initially we're empty, but we have room for more because we want to make sure we can do the correct geometric doubling. All right, someone said project 4, so we'll take the number 4. Let's put 4 in first, and then we'll add 42, and we'll add 31. Remember, the default here is adding to the end. Now, with a list ADT, you can add at any given index. Remember, there's an insert at a given index operation you can do. So if you want to put something at the new index 0, you can. So if we were to add a new number here and we wanted it to be index 0, what needs to happen is 4 needs to shift, 42 needs to shift, 31 needs to shift. Right? To put in a new value, how about 34? I like it. We'll put in the new value there at index 0. So everything has to shift. So in terms of the size of the data structure, the size of what we're storing, and how many operations it has to take, anytime you insert at a given index, it's going to take the... It's essentially the math is, it's the index here, it's the n number of items, right? N items minus the index. Operations, index, there's an n in there. Sure, index, I can't spell, index. So n minus index operations to insert at a given index. So if you're inserting it near the end, right? Sure, we only have to shift one thing. We can remove 54, or put in 54 and move 31 here. That took one operation to move and one operation to insert. So to remove an item, you do the opposite. So if we wanted to remove, say, let's remove here. So this was add. ADT, and then remove is the same. So if we wanted to remove index 1 here, it's n minus 1 operations, because I'm going to take the 4 out, so we're going to remove the 4, and we're going to put 42 in its place, put 54 there, put 31 there. So it'll be 34, 42, 54, and 31. So removing something at the end is really quick, because nothing has to shift. Right? But removing something close to the beginning means it takes n operations. And because we don't know what k is, right, or the index, we don't know what index is, n minus the index, again, index here, because it could be anything on average here, right, we just assume it's the middle, and, that means that's half of n. And remember, when we talk about this big O notation, these coefficients, the constant values here, they get thrown away. So it's still an O of n operation, because the more n items you have, the more shifting that needs to happen to keep things in an ordered fashion. Because with a list ADT, the order matters, and we're going to maintain the order. So we might take things out and remove things at given locations, but we'll maintain the order. So that's what's interesting with the list ADT, and that's what the array list does. Right? Our array list. We're not going to write our own array list. Right? Array, that's an A there. Array list that we've used, because array lists are much easier than basic arrays because they're resizable, right? You can always add to the end. You can just keep adding. So if we look at an array list of, I don't know, type integer, sure, my numbers equals a new array list here, and then we'll add our import. Thank you, NetBeans. Yes, please. We can see numbers dot, and we get all these methods here. Numbers dot. There we go. You can add at a given index. You can see if it contains an item. You can go through each operation. You can get at a given index. So an array list is a list. It's a array-backed list. So what that means is we know some of these performances. So for adding at an index, it's O of n. For adding at the end, we know that's constant. So if you're guaranteed at the end, you know it's constant on average, because we do that amortized average where, sure, sometimes we have to double the size and shift a bunch of items, but it only happens geometrically. Some of our math hand waving. You can remove at a given index, or you remove an object, O of n operations. You can set the value at a given index if you just want to change the value instead of remove it. Right, so we've got all these operations we can do with the array list built in because it's an array-backed storage. Like when we did our bag, we had that array bag. Okay, so we don't need to do too much with the array-based storage here, because we hopefully that one makes a little bit of sense after we've talked about the array-based bag. So we're going to kind of gloss over that one. Again, implementing it yourself is not that interesting. It's essentially the array bag code that we did, but then we have to add methods for insert at an index, and we have to add methods for removing at an index. So it's not too much more without too much trouble here. What we're going to do is we're going to write our own linked list. So remember when we did the linked bag, we had this idea of a node, right? And we had a node here, node, and a node had some data here, right? It stores the data here, and then it points to the next node. Okay, that was the linked bag, where we stored the data itself, and then we stored where the next node is, right? So we had more data, and we had the next, and then we had data, and then the next. I don't know why those are getting taller and taller. They don't need to be taller and taller. Right? More data, and the next node. And eventually there was nothing at the end. It was null, was how we knew we were at the end. And what was cool about linked nodes is you don't need to get a big contiguous block of memory. Here, you don't need to have that instant access to sequential memory. So there was never resizing that happened. Right? We were guaranteed our operation performance. Even the worst case was still constant time, where the worst case time with an array is O of n. Remember, when we talk about usually there's best, there's average, and there's worst case. We don't usually care about best because, that only happens in the best situation. So most of the time we care about average, and worst is important to know, but usually average is the best one, right, to focus on. So with the linked-based storage, this was great. And we had a linked bag. Right, we just could keep adding things to the front, right? Making more. It was nice and easy. Now, removing items was a little bit trickier right? You go through and remove a particular item. We had to do this jumping where we point to the next thing, and that's where the tricky part happens here. And so what we're going to do to make this easier, because remember, when we only had the pointers to next here, we had to we looked at what was the next data. If that wasn't null, then I could do something, because if we had to remove it, we had to point my next to my next next. Right? And that was a little bit awkward. Not the worst thing in the world, but it was a little bit tricky. So what we can do is we can make what's called a doubly linked list. And a doubly linked list means that you have nodes here that look like this. They have the data, they keep a previous node, and they keep a next node. So previous is what comes before me, next is what comes after me. So that way at any given node here, we're going to have links to the previous and the next. Data and next. Right, and then these ones, I don't know why I keep making them taller. Previous, data, next. Right, so for any given node, you can find out the previous here, or you can find out the next. The next's previous will be yours. So the syntax is going to get a little funny here, but we'll be able to figure this one out. Okay, so that's what we're going to do. We're going to do a doubly linked list to look at a list ADT with links. And what's great about that, again, we still might have some performance issues, but when we get to the interlude and we talk about iterators, we're going to see a huge performance gain. So with a linked list, right, adding to the front, or when you looked at like dex here with a linked operation, you could add to the front or you can add to the back in constant time, because we already knew where the front and back were. So we could put a new node here at the front and say, okay, your previous is now a new node here. Boom, previous, next, previous data, next. Right, we could set that up here at the front. We could add one to the back, no problem here. Right, previous, data, and next. Right, just keep adding more links in the chain. Now, adding in the middle gets tricky. So if we want to add at the given index, we have to start at the beginning and we have to count, or we have to walk these paths here, because I can't say, hey, give me index 7. Remember, with an array, you can jump right to index 7 because you get to do that arithmetic. Hey, what's the size of my object times 7? Go from that memory address up. With a link node, we can't do that. We have to walk these links here. So we say, okay, starting at the beginning here, let's walk 1, walk 2, walk 3, walk 4. You can just follow the pointers next, 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 until you've gotten to the index you want. So the slow part is getting to an index. But once you're at an index here, once you're at a given position, adding and removing is constant time. Because you just have to add something. We'll say if we wanted to add it between these nodes here, we'd build a new node, previous, data, and next. Right? We'd say, okay, my previous is going to be what your previous was. My next will be yours. And then I need to change the ones around me to include me in the chain. So I'll say, hey, my previous, your next isn't what it is now. Your next is me. Hey, my next, your previous is now me. To break those links in the chain. Now we've inserted ourselves into the linked list. It's really easy. To remove something here, we just need to jump. So say we wanted to remove this node here. We say, okay, hey, thing that comes before me, your next is now my next. Hey, thing that comes after me, your previous is now my previous. Boom. So we take out those links in the chain here. So things no longer point to us, and then we just null ourselves out. We're gone. That's how we remove a node. So once you get to a position, that's really quick. If you don't have a position, right, to add an index, right, is again n minus the index. It takes n operations to get there. And you can do a little bit of optimizing here, which is fun, because we know the front and we know the back. So we know it's at no more than half of n, right? Because if it's less than half, I'll start from the front. If it's more than half, I'll start from the back and count backwards. In little optimizations, but still, we're only getting to 1/2 of n, and we still throw away the half for adding and removing at a given index. To add to the end, or add to the front, constant time. Right? With an array list, adding to the front takes n operations, right? N minus an index. Well, when the index is 0, that's n operations. But adding to the back is constant. So adding to back is faster than array list, but adding to front or back is constant with a doubly linked list. So we're going to work on the doubly linked list. This is a really fun one to write. So we're going to add a new class. Now, the book goes through and he has all sorts of cool interfaces and things that he implements, and I find that a little bit confusing. So we're just going to do our own here. So this is a doubly linked list. Okay, and doubly linked list then makes use of a class for node. And the class for node, we should just do public here because this is a private inner class, so no one else has access to it. So we can have a public node previous, we can have a public node next, and we can have public T data. So this is a node of type T here. Right, and then we can write a constructor. So node here. Then how about a T data? How about a node previous and a node next? Right, this data is the data. This dot previous is the previous. This dot next is the next. And then just to make life a little easier here, right, we can add another constructor. So if we only have the data, I mean, we're always going to have previous and next, so let's not worry about it. You could add another constructor that you just give data, and previous and next become null, but we'll see we're not going to need that later. So doubly linked list of type T here, right, a generic, so it'll hold any type that you want to give it here. It's perfectly fine. Excuse me. And what we're going to find here, so we spent a little bit of time when we talked about queues with this idea of a circular queue. Remember where we could just be in a circle here? So the front and back were actually always at the same spot here. And you just add here for the back, you'd add here for the front, and it would just maintain a circle around and around and around and around. This is going to make life way easier. So the book goes through the hard way, and then it shows you the easy way. And I'm just going to skip right to the easy way. So what we can do is we keep a dummy node. We keep like the start node or something, or the head node. I don't know, whatever you want to call it here. I'll call it the dummy node. So the dummy node, then, when we start a linked list here, it has no data. Its data here is null. Its previous and its next. Its previous is itself. Its next is also itself. What's really cool about this is now as we add things, if you want to add to front, the dummy node's next is the front. So dummy node next equals the front, the first node. The dummy node's previous is the last item, or the back. We'll call it back, right? So to add to back, you add between the previous here, right? If you want to add to the front, you add to its next. So what we're going to do to add something here, right? We said, okay, you go in between where you want to add them, and then you change the operations, right? So to add here, so if we wanted to add at index 0, we become the dummy node's next. Great, easy. Or even adding to the back. The operation's still going to be the same. So we create a new node, right? Its next is the current dummy node's next, right? Or the current 0, that index's node next. Okay, so its next becomes this one's next. So we're going to add a new node here. We'll add some data. Its next is what this one's next is. And then its previous is the dummy node. Then we have to go fix things up. We say, okay, hey, thing that comes before me, I come after you. So now it's no longer going to point at itself. It's going to point at the new node. And then, hey, and it says, hey, thing that comes after me, I come before you. So its previous is no longer there. Its previous is now here. Now we're in a nice circle. The same thing for adding to back. If we want to add to back, we'll make a new node back here. We'll put in some data. We'll say, and next, hey, the next thing for the last item is the dummy node. Its previous thing is its current previous. So my previous then will be this one. And then we have to fix it up. We have to say, hey, thing that comes after me, I come before you. So the previous link breaks here. It says, oh, okay, I come before you. And we say, hey, thing that comes before me, I come after you. So we break this link here. And now we come after this one. So we're maintaining all these links here. Right? And as long as we have a dummy node, it's really easy. We don't ever have to check for nulls and check to, hey, as long as the next is not null, this sort of thing. Life is going to be really good. So we're going to have a private node for the dummy node here. And we'll make a constructor for a doubly linked list here. And we'll say dummy node equals a new node, given null for the data, null for next, null for previous. Then we can go fix those up. We can say dummy node dot next equals the dummy node, and we can say dummy node dot previous equals the dummy node. Because what we want is we always want these next and previous links to have values. If those are ever null, we run into trouble. We're also going to keep a int size, maybe? Or number of items? How about number of items? Number of items. And then my number of items will equal 0. Again, the constructor's job is to give all of our attributes values. Okay, we're going to add a public int, I don't know what size. Return number of items. Easy. How about a public boolean is empty? We're going to return number of items equals 0. Now we don't need to say if this equals 0, return true, else return false, because remember, this here is a boolean statement, an expression. It's either true or false already. I don't need to say if true, return true, else return false. I can just return the statement that is already either true or false. Okay? And then we'll add a public void add, a t data. So adding here, this is the add to end. Right? And remember, the last item in the list is the dummy node's previous. Remember, when you add to the end, the dummy node's previous is the last thing. Okay, so we're going to make a new node. So node, new node equals a new node. We're going to give it the data. It's next then. Right? If it's the last item, I'm sorry, its previous is going to be the dummy node's previous. Right? What used to come last here now comes before me. What comes after me is the dummy node. Right? Because I'm coming after the dummy node. Okay? So we're adds a new node. We're in that location. So, right, if we want to add a new last thing, we'll add a new node over here. Here's some data. Let's say our previous is the dummy node's previous. Previous is here. Our next is the dummy node. Great. We're in the right location. Now we need to get everything around us to point to us. So then we'll say, hey, my previous next. Don't point there anymore. I come after you. Hey, my next previous. Don't point there anymore. Point to me. We've inserted ourselves into the link. Okay, so then new node. This is where it gets a little silly, but it's okay. New node previous next equals the new node. New node next previous equals the new node. Right? The previous is a node, previous has a next. Next is a node, node has a previous. So this syntax looks really silly, but it's just connecting the dots here. And then we'll take our number of items, plus plus. Okay? And then we'll do a public void add, given an int index, and a t data. If you want to add yourself, add a given index. First, we're going to check if the index is greater than the number of items. We're going to throw a new index out of bounds exception. Okay, right. Make sure, hey, a bad thing happened. No, you can't do that. Now, if I have 10 items, we're going to say you can add yourself at index 10. That's just a regular add, right? No big deal there. Okay. So then we can check for that real quick because that one's really quick. So we'll say if index is equal to the number of items, then we'll just call add given the data. Okay, because otherwise my counting is going to get off really funny, right? Else, then, the other case, right? Aside from that, I need to start counting, right? I need to get into that position here. So the current node, we're going to say node, current node, just like we do with the bag here. We just have to walk these nodes here. The current node starts as the dummy node. Okay? And then we're going to start walking those links here one at a time here. So we'll say for int current index is 0. Current index is less than the index. Current index plus plus. We're going to say current node equals current node next. Right? Go to the next, go to the next, go to the next. Again, we could optimize. We could do, hey, if we're more than half of the size, then start at the end and walk backwards, but we don't care about that right now. Not a big deal right now. Right? That's a future optimization. Right? Should we leave a note? Future to do future optimization from back if index greater than 1/2 of number of items, 1/2 of size. Sure. We'll leave ourselves a little note here. Okay? So we're going to walk to the next, the next, the next, the next, the next. So given this link here, right, this one is index 0. Right? Its next here is here. This one is index 1. Its next is here. This one is index 2. So if I wanted to put myself at index 1, I'm going to loop. So I start here. Right? This is current. 0 is less than 1. Yes, go to the next one. So now this one is current. Okay, and I want to become the new index 1. So I'm going to go in between the current 0 and 1. So I could do index 0, I could do index 1, I could do index 2. Right? Easy. My size is 3. If I said, hey, I want to be at size 3, we just do it add to back here. Easy. The counting should still work either way. I guess that would work. So this would be 1, this would be 2, this would be 3. Yeah, we can ignore it here. I guess then it'll just make life easier then. We'll forget that. We'll forget that. This will just make life easy. We have too many curly braces? Are we good? We're good. Okay. Once we get to where we need to go, we're going to make a new node. So new node is equal to a new node given the data. The previous then will be the current node. The next will be the current node's next. Right? And then we add ourselves in between. We do the same 2 lines of code here, the same 3 lines of code here. I'm going to feel a little bad we are copy pasting here. Right? We can fix this up later if we want. Right? We can fix it up. You know, let's do it right now. We have it in here twice and I'm feeling bad about it. So let's do this twice. So we'll have a private helper method here, right? Oops, too many curly braces. I thought we did have too many. Oops. So a private void add between given t data, the node previous, node next. So if you tell me, hey, what data add, what comes before it, what comes after it, right? I'll make a node, new node, equals a new node, given the data, the previous, and the next. And then I can do all this stuff. Right? Its previous next is me, its next previous is me. Great, we're good, we're good, we're good. So then what we do then, we just call add between, given the current node and the current node's next. It adds between those, right? For adding here, well, we're going to add the data between the dummy node previous and the dummy node for adding to the back. Right? See how that makes life easy? And again, this is just a private helper method because no one else knows about nodes. Only we know about nodes. So we just need to walk, right? We need to get to the location and add ourselves in between those 2 links. That's to add at a given index. Okay? Now how about remove? Public t remove, right? A index. I think that was it. To remove a given index. Again, we have to do the same thing. We have to walk to that location, to where we're going to remove. Again, probably do the same check. So if we're going to do this more than once, all right, let's make that a private helper method. Private void check for valid index. Index. Sure. We can remove at a given index. Now, now this one, okay, I guess that's actually bad. Let's just say if it's greater than or equal to the number of items. We'll just throw, because otherwise remove, we don't have an index at that location, and I'm feeling bad about it. So if you'd go to add at index 3 in this position, we'll just say that's invalid. We don't have an index 3. You could just use the add method instead. And I think that's fair. Okay? So then add has to check for valid index, given the index, great. And then I can do this new node thing. It can walk here, right, to a given index. Right, give me back the node. Right, so remove at a given index. Great. Well, if we're going to do this exact same thing and give me back a node. Right, so we might as well make another private helper method here. So let's pull that one out. We'll make a private node. I don't know, walk to index, given an index. Node is the dummy node. We get there, and we'll return the current node. Okay, so we'll walk to the given index. You know, this way, if we ask for 0, it won't give me 0, though, will it? Maybe we don't want that. All right, that's fine. Maybe we don't want that. We'll undo. I think we can fix it, but not right now. It's not going to make sense right now. We're going to do the same thing here then. We'll do the walking because we need to go find which one we're going to remove, but I want to get to the index. So as long as we're equal to the index here, we want to get to it. So index 0, we don't want to remove the dummy node. Right? At index 0, we want to get to index 0 and then remove. Okay? I like that. Okay? Once we're there, then we're going to take the t data will be the current node dot data, and then the current node's next previous needs to be the current node's previous. Oh shoot, this is a node of t. There we go. Current node. Ah, that's important. There we go. New node of t. There we go. You gotta make sure we're using the right t there. Okay, node of t. Okay, I like that. Node of t, here we go. Node of type t. Okay. That ought to be better. So my next previous is my previous. My previous next is my next. Right? Take myself out of the chain. Right? No, nothing's pointing to me anymore. And then the current node data, we're going to null that out. Right? Make sure we can garbage collect everything. And then we'll return the data. Also number of items minus minus. Right? Take away one of our number of items. Okay? We all right so far? So we'll walk to the node, take it out. Right? Jump over it. Do the removing. So that the thing that comes after me points to my next. The thing that comes before me points to my next. The thing that comes after me points to my previous. Take ourselves out of the list. Here we go. We can fix this up now. I remembered. So we want to private node t walk to index, given an index. Turn the current node. So then, here we go. This is add, remove. So node of t, current node is equal to a walk to index given the index. Okay, do that. Now, for this one here, when we're adding, we just need to change this up a little bit. So instead of saying my previous is the current node, and my next is the current node's next, if we go one more, if we do that same walk here, walk to index, given the index, so if I wanted to be at index 0, and I'm at index 0, my previous needs to be the current's previous. And then my next needs to become the current node. And I'll add myself in between them properly. And I think this check for valid index we can do in these walks as well. We can do in a walk to index, and we can do in a add between. Because those checks should happen there. Then we don't need to check for them inside the methods here. Right, we just add between. We'll add between. Once we walk to the index, we'll walk to the index and we'll remove. Right, if we just want to remove a t remove removes the last one, then right, if we're going to remove the last one, we can do that same operation. Yeah, we're just going to take the current node was the next previous, I guess. I guess we should check if not empty. If is empty, throw invalid index. Index out of bounds exception, sure. We can't remove if we're empty. Throw a new one of those. Otherwise, hey, well, what do we want to remove? Well, let's take all this out here then. Okay, this will be a remove node. private t remove node, given a node, current node. Node of t, current node, there we go. Break the link, remove the number of items, and we'll return the data. So to remove at the index, get to that index, and then we're going to have a t data is going to be remove node, given the current node. Get back the data. To remove without that, then we're going to return remove of, oh, that wants an index. So we want to do remove node, given the dummy nodes previous. Right? Whatever the previous is the last one. Remove node, oh, what's the problem here? Node of t. All these have to be of type t. Remove node is a t, that's a t, right? Where did we go wrong here? T remove. Object cannot be converted to t where t is a type, t extends object. Let me know it's, oh, yeah, that should be previous, should be a node. Node of t, sure. No, all these are nodes of t, right? Node of t, node of t, add data, node of t. Why does it not like that one? Remove node should give me back t data. All right, let's try this. Node of t, current node. Previous. Okay. For some reason, it didn't like that all in one line. I don't know. We just have to declare it here as a node of t, and then it should be happy. Right? Because current dummy node's previous is the last item. I know this is a little fast, but this is this idea, right? Having these double links here lets me just pick my next and my previous as where I go, and then my next's previous becomes me, my previous next becomes me. We just link ourselves into the chain here. So the problem is we have issues until we have a iterator. So the iterator is where we get in the interlude, and the idea with an iterator is I know what position I'm at. Right, so the idea here is that I'm actually going to give you an iterator so that you can maintain your position. So if you have an iterator, right, it lets you loop over the list. And we're not actually going to write this one out. This is a fun exercise and all, but it's just adds a whole lot of extra wrapper code. It's not too much, but I think this is enough. If we add the iterator stuff, it's going to be a little confusing. But the idea with an iterator is that if I can maintain my position, inserts and removes are constant. So say I were to add like a bunch of different items here. We just add a, I don't know, we had a bunch of like 7, 42, 31, 23, 57, on and on and on. We just had a bunch of these, right, in a loop here. We'll just keep on going. Pretend it's like a circle, right? 49, 1, 7, again, right? It doesn't matter if we have duplicates in here. 12, 52, 91, and 100. Right? If this was the start here and this was the end, right? We'd have our little dummy node in here, right? Our next would be this one, our previous would be this one, and these are all nodes, right? These are all doubly linked nodes. If I get to a given position, if I'm iterating through and go this one, and then this one, and then this one, and then this one, and then this one, if I hold this position here, I can add and remove from that position in constant time. Because I just need to add a new link to the chain over here, or add a new link to the chain over here. You throw some more numbers in, right? 27, 10, I don't know, throw numbers in. At that position, add before, add after. So with a positionally doubly linked list, when you have a position iterator, you can add or remove at a position in constant time, no matter where you are in the list. So when you're dealing with lists of data, if you're adding and removing a whole lot at given positions, this is going to be way, way, way faster than an array-based list, because the array-based list, adding and removing at a position is always O of n for adding and removing at an index. even if we have positions in arrays, because everything needs to shift in the array to make room for that new item. With a positional linked list, we can add and remove from a given position in constant time. So we still need to get to that position, but then we can add and remove from it in constant time. So it's super fast for adding and removing at a given position. And even if you need to shift a little bit, maybe we walk a couple positions, not too big of a deal. We can get to a position in O of n time, right? Whatever that position happens to be. But once we're there, we can add and remove constant. So we get really fast add and remove operations. That's what's really cool with a linked list. So depending on what your data is doing, if you're adding and removing a lot, a linked list might perform better than an array-based list. As much as I love array lists, linked lists are great for that sort of thing. Does that part make a little bit of sense? So once we have a position, you can add before it and after it in constant time, right? O of 1. O of 1. Right, those are terrible. O of 1. Because we know what that position is. So that's the big benefit of linked lists. Again, it's going to depend on what we're doing with our data. Right? If we're moving all over the place, if we're going to the front, to the back, to the front, to the back, to the front, to the back to add and remove things, we're not getting a whole lot of gain. The other crazy thing you can do is you can keep multiple positions. As you iterate over it, you can have multiple positions in a list. So you can have like, hey, here's my front position over here. Here's my back position over here. Here's my mid position over here. So you can add and remove near those by trading a little bit of memory. By keeping more positions in memory, we can get near different locations to add and remove really quickly as well. So even if you're doing lots of add and removes, like if you're at the front or the back or the middle, if you keep that position front, you keep a middle position, you keep a back position, you're holding a couple more positions in memory, but you can add and remove from those locations really quick. So, you might have some number of positions based on the size of your storage, right? You get lots of options around how you can optimize for add and removes at given locations, which is really cool. At the trade of a little bit of memory. And then it's still a list in which your position, your order is preserved, which is super cool. So let's try it real quick, make sure it works for us here. So let's make a doubly linked list of type, how about integer, right? We were doing numbers before. Numbers equals a new doubly linked list. And then numbers dot, let's just add, we'll add a couple here. How about 10? I'm going to put them in sorted order because it's going to make life easy for me to see if it's working here. Okay, and then we'll do numbers dot add. How about at index 1? We'll add 15, right? That should go in between the 10 and the 20. Right, let's try adding at position 7. So 0, 1, 2, 3, oops, 4, 5, 6. Oh, no, we don't want 7. How about 5? So this is 0. This is 1, 2, 3, 4. It'll become the new 5. So let's add like 45 there. And then we'll say while numbers dot is empty, while not is empty, let's just print numbers dot remove. How about we remove 0? Right? Let's remove index 0. We should get back in sorted order. See if that works. We're just going to test it out. Writing a unit test would be better, but we're going to try and... Oh, what didn't compile? Oh goodness, where's our error? Uh-oh, index. Oh, we don't have an index. Let's add between. Oops. Where do we get that from? Let's add. Okay. Oh, walk to index needs to check for that. That's right. Walk to index checks. Okay. So we're good. We're good. Now it might run. Let's see. Do we get our numbers out in sorted order? 10, 15, 20, 30, 40, 45, 50, 60. So it looks like we're maintaining that order properly. We were able to remove them. Cool. That worked out pretty well. Now let's see. That removed 0. Then if we just remove from the back, do we get in reverse order? 60, 50, 45, 40, 30, 20, 15, 10. Looks like we got it. So removing from the back seems to work with our defaults. So I'm pretty happy with it so far. Again, we haven't done tons of exhaustive tests yet, but I'm pretty happy. Not too bad. What do you folks think for a doubly linked list? All right, GG's. So this will take a little time. Spend a little time looking at it, thinking about it, kind of pondering through it. Again, we did the array-based stuff with the bag. We just need to maintain order. So here's the linked version where we're maintaining order instead of the linked bag. Okay. Then what's cool is if we wanted to have a sorted list. With a sorted list, you can't add at a given index. All you get is an add, and we're going to find the correct location for it to go. Right? So imagine we had a bunch of numbers. We talked a little bit about sorts, right? The idea of an insertion sort and a selection sort. We're basically just doing an insertion sort. Right? Whether or not we're using an array or a link, either way, we need to find where it is. So we're going to have our list of numbers like 7, 12, 19, 27, 42. You give me any number to add, and I'm going to start here and say, hey, if it's less than, add before. If not, go to the next one. If it's less than, add before. Nope. If it's less than, add before. Nope. If it's less than, add before. Nope. If it's less than, add before. If it's not, you get added to the end. We're just doing an insertion sort. We're inserting it at the correct location because we know our list is in sorted order. So you get less functionality with a sorted list because you can't add anywhere. Now you can remove from a given index, sure. Or you can remove an item, go for it. Have at it. Okay, go find the item and remove it. Okay, so sorted list is great. And you can do it either with arrays or with links. Now, it's still going to take n operations because you have to find where it is to find the sort. With a linked operation, right, it's O of n. What's really cool is if you have an array-based list, you can find it faster, but you still have to insert. So inserting at a given index is still slow, O of n, but you can find it faster. So if these were in an array here, right, what you do is you'd start at the middle and say, is it too high or too low, or do we find it? And you cut either half of it off. So if we're going to add 20, we say it's bigger, so we cut these ones off and say, okay, now let's take the next middle. Again, we don't have a middle here, so we just pick one of them. Is it too high or too low? And we can add it right in between. Works out pretty well. So you just keep splitting the difference. So if you have 100 items, you guess the middle. If it's higher than that, well, you're in the next half. If it's lower than that, you're in the lower half. So each time you check, you're removing half the items all at once. That's a cool thing you can do with a sorted. But again, if it's an array, just because you can jump to that middle index, you still have to, if you're inserting there, it's still going to take those n operations, or half of n, whatever it happens to be on average. So it'll still be slow. All right, I think we're good for the list ADT for now. It's a little bit more about iterators. You're writing your own. It's not super interesting to write your own iterator. It's all about that position idea here. And then the sorted list, again, just maintaining your sort, whether or not your links are arrays, and finding where that next item needs to go. All right, so we can do a little bit of midterm review and then talk about project 4. I think that was the vote, right? Midterm review second, and then project 4 last. All right, don't forget the sorting quiz and the queues, decks, and priority queues quiz. I have those due by Friday, so I can get them graded before your midterm. I'll get everything in. I apologize for the delay. It's been just a really rough summer. My apologies. I know it's no fun to have these things outstanding, so I'll be working on getting these in for you. And then you should be good. You should be able to review them for the midterm. Similar style questions for the first half, and then those long answer style questions for the second half that we talked about up here. So we should have our midterm review. Let's see where to go. The questions will be similar to the quizzes, so I don't think you need to study the quizzes, but just like that's the style of question and the topic, right? The same sort of quiz style questions. Here's a short answer or a true false, if false correct the statement about it. Why won't that load? Come on, load content. Let's go D2L. There we go. Our midterm review, come on. All right, so a stacks and queues question. Let's start with a new project here. We'll do midterm review. So we're going to write a quick trick stack queue that accepts a number for numbers from 2 up to including the number passed, put them into a queue of stacks. If the number is prime, put the current stack on the queue, make a new stack, add the number to that stack. If the number is not prime, add it to the current stack. Yeah, yep, I'll post it in GitHub here. All the code is going to go there. Yep, I guess I should do that doubly linked lists first. 53. We don't need any of the midterm review stuff yet. That's list ADT. Hit and push. There we go. Awesome, awesome. All right, so for the midterm review, that method, what does it call it? Public void quick trick queue stack or something. Is that what I called it? Quick trick stack queue. Quick trick stack queue. Give it an int number. All right, for the numbers, right? So for int n equals 2 and it's less than number and plus plus. Then what we're going to do, we said, if the number's prime, put the current stack on the queue. Make a new stack, add the number to. Okay, so we need a queue here then, right? So we need a queue of type integer, queue, a new queue, java.util.queue. Cool, we got a new queue. Oh, that's right. That one's abstract. We want, I don't think it matters, a new I don't know, linked queue? Is it linked queue? I think we can do that. Nope. Util.star. Which ones do we get here? Which kind of queues do we get? What implements queue? Oh goodness. All right. I was just Google. I don't remember off the top of my head. My apologies. Java queue class. These sort of things aren't worth remembering. A linked list implements queue. Sure. Here's the queue interface. Let's see. An array deck. Sure, we can do that. A linked list. Sure, we can do that. Look at that. They even have a linked list for us. We do the linked list. Why not? Linked list. And we're just going to use the queue type here for our queue. Okay, and then we need a stack, right? So a stack of type integer. Stack equals a new stack. Okay, and there's a stack already in the Java API. Right? We don't need to use our own. We don't need to write our own. So if the number's prime, so if is prime of n, we're going to put the stack onto the queue. Oh, I'm sorry. So the queue is actually a type of stack of type integer. There we go. Queue dot add the stack. And then stack equals a new stack. And stack dot push n. Right? Actually, either way, we're going to add the number. Okay, so if it's prime, make a new stack, right? Put the current stack on the queue, make a new stack, add the number. If it's not, add it to the stack. So either way, the number is going to add it to the stack, but whether or not we're making a new stack or not is if it's prime. So the only thing we don't have is prime. Okay, so I don't know, let's go Google. Java is prime number. Check. Which one? Which one looks decent? Java? Sure. Why not? Java point? Okay, sure. Ugh, that's not a method. Not a method. Check prime. Here we go. Why is that void? That's ugly. Goodness. That's a terrible one. Program is? Program is? Right, I'm worried about this one now. Goodness. Why do they not have methods? Those are all awful. Those are awful, friends. Geek for geeks. Come on. Gotta have a hit here, right? Here we go. There. Done. Here's a method. Is prime. And we're going to cite our source. Right? We're going to say, hey, I found it here. Right? Sure. Boom, done. Question's done. Right? And the solving is prime is not what you need to do, right? Just find something that looks like it's going to work. Maybe make sure it works. Some people have given me some weird stuff before, but that should be fine. Okay, you can optimize this, right? You only need to go up to the square root of n. You don't need to go up to n, or even half of n, right? Because you're not going to find any factors if you haven't gone through the square root, but you need to round and things like that, so don't worry about it. That's how I can tell if most people steal their code for things and don't cite their sources when they add in those optimizations, like checking for the square root of n, round it up, math.ceil, because nobody else does that, right? And unless you found it online, you're not going to know to do that. It's math. Okay. Sure, how about we return that Q? Why not? Return the Q. Why not? Again, we didn't really ask for it, but that's fine. Right, and then if you want to test it, you could test it, add a bunch of numbers, and see what happens. Right, pop out a bunch of numbers. But that's it for now. All right, recursion question. Write a function number checker that accepts the number. Print the number. If the number is even, add 1 and recurse to the new value. If the number is divisible by 5, recursion ends. If the number is odd, double it and recurse. All right, so we're going to write a function. Public void number checker. Give it an int number. We print the number. Okay. If the number is even, add 1 and recurse. So if number mod 2 is 0, that means it's even. We're going to recurse with number checker, number plus 1. Add 1 and recurse. Okay? Else if the number mod 5 is 0, we're done. That's it. Right? Recursion ends. Otherwise, if it's odd, right, the other case, right, we're done, return, boom. Else we're going to call number checker of that number doubled. Number times 2. Unnecessary return statement. Fine. What, we just leave it blank? I guess. I don't know. Whatever. All right, let's try it. So we'll call number checker. Oh my goodness. Public static. That's why. Static void. We call number checker given, how about 10? So 10's even, we should get 11. 11 is odd, it should get doubled to 22. 22 is even, should add 1, we get 23. 23 is odd, we double to 46. 46 is even, we add 1, we're at 47. 47 is odd, we double. Oh, let's see what we get. Oops, uh-oh. Integer. Oh my goodness, I can't spell integer, folks. Okay, let's see if we can number check 10. Uh-oh. What are we doing? What's wrong? What's wrong? Illegal start of type. Line 28. Q, like this. Should be the diamond operator, right? No? Oh, goodness. Okay. Can we build? What do we get here? All right, that built. Weird. No? Did it not build? Did not build. Fixed the integer thing, didn't I? Line 28. Queue of stack of integer. Stack of integer, new stack. Do that at the stack. Stack to new stack. Why is that so unhappy? Clean? Maybe clean and build? Save? Yeah, I'll try saving again. Says it did it. Super confused. Alright, that was... Okay, it worked. Weird. Alright, look at that. So we get up to 95. Cool, so that seems to work, right? Odds get doubled, evens get added 1, doubled, add 1, double, add 1. Divisible by 5. So our quick trick stack queue, I guess it's a queue stack. Maybe a queue of stacks. Maybe I named it wrong. Just having fun with queues and stacks, right? Pushing, popping, doing whatever. Oh no, that's the number checker. I'm sorry, we didn't even do the quick trick stack queue. Got to do that one. All right, and then the last one here, our priority queue implementation. Write a class long strings that implements the comparable interface. Long string should have a private attribute for message. When you compare the length of the message string with the length of other string. Ask you for 5 sentences, create a long string out of each sentence, put them in a priority queue, and print them out in sorted order. So long strings. A new class for long strings that implements comparable of type long strings. And it says, no, you don't. And we say, yes, we do. Implement the method. Okay. So private string, sure, why not? And public long string, given a string for string. This string equals the string. Long strings, there we go. Strings. Yes, just long string. Right. We probably don't need the plural. And then a public string get string. Return string. Sure. And then compare to. We're going to return string.length minus other.string.length. Right. Length is a method, Paul. Sorry, length. Okay. We'll compare the strings. Maybe just two string. I like that. Call that an override. There we go. Two string. Sure. What's wrong with that? Long string.java. Okay. Oh no, I put in the wrong package. Put that in midterm review. Refactor. Refactor. It's fine. All right. Long string. There we go. Type of long string. This is what I get for renaming things. Should have left it with an S. Okay, now it should be happy. So make a priority queue of them. So priority queue of type long string. Here's my strings equals a new priority queue of type long strings. Awesome. We'll add a couple strings. So strings.add a new long string given I don't know, test add 5 strings, right? We're supposed to ask the user for 5 sentences. Sorry. Okay, so for index or I don't know, sentence count is 0. Sentence count is less than 5. Sentence count plus plus. Asking for a string, so we need a scanner keyboard equals a new scanner. Given system.in. And then we'll ask them, enter a sentence, and then we can take my strings, and we can add keyboard.nextLine. Okay, we'll do that 5 times. Add a new long string of keyboard.nextLine. Make a long string to add it in. And then while my strings.is empty, while not is empty, we're going to print my strings.remove. Right, give that a run. Oh goodness, did it not? This compile and save thing is the worst. It's nice when it works, but it just doesn't work for me most of the time. Ever since I reloaded, actually. Wonder if that's must have something to do with it. Alright, so give it some sentences. So testing, hi there, this is really long and short. You get test, short, testing, hi there, this is really long, right? So the shortest one goes to the top with a priority queue. Looks like it works. Okay, there's our midterm review. Any questions, thoughts, concerns? I'll post all that as well. Midterm review. And similar style questions. So something about stacks and queues, something about using a priority queue where your class will implement the comparable, and we'll go do something with it. Right, and a question on recursion. All right. Thoughts on assignment 4, project 4? If I can ever get this to load. Maybe I can get it to load. Project 4. Again, this one's not due till the 21st. So that is in 2 more weeks, right? Because we have midterm next week, and then the week after is when this one will be due, 6 p.m. We got some time to work on it still. Come on, D2L. I think my connection is fine. I don't know. Refresh. What's going on with this? Is it D2L? Is it me? Hard to tell sometimes. All right, we'll clear this one out. Close that down. I wonder if I'm just running too many things. Close that down. Come on, D2L. Close that down. Up heap and down heap. Yeah, definitely. Yeah, the priority queue is, I wrote it. Yeah, I mean, you could use the Java library priority queue. I mean, that would, like we just did, that one's already built. It's just looking at how it's done is much more interesting, especially with that tree structure. It's really cool. So you get really good performance. Why is this not loading for me? Friends. There it goes. All right. All right, our hospital cafeteria lunch line. Right, nurses first, then doctors, and everyone else. So someone had asked, and I think I posted in the Discord, you want to, once they're ordering their food, like, take them from the front. Right? So you should take them off of the queue so that if you go and add someone who would jump to the front, they're not already there. Okay? Because that way, like, if a doctor's in line and the nurse joins, she would go to the front because she has the highest priority, and then the doctor would have to wait. But if you've already taken the doctor's order, then you don't want her to have to wait, like, because she already put her order in, and then the nurse jumps in, and then she'd be there, and then the doctor, like, so whoever's at the front, once the order's done, take them off the priority queue, let her order, and then let the next person join. Okay? Does that make sense? So this 120 minutes, just 120 times in the loop, where each time in the loop is a minute, right? Using the priority queue. Appreciate, you could check maybe in the Discord or the discussion board maybe. I'm not sure. I know not a lot of people are doing it asynchronously, so we don't usually have a large crowd here in chat. There's only a handful of people here currently in chat. All right, we're closing in on near the end of the semester. We'll do the midterm next week. We'll get into sorting, dictionaries, and hashing. We'll finish up hashing, talk more about trees, binary search trees, heaps, balanced search trees, graphs, and then we'll get to the final project. So we'll talk about what it is. You'll get it assigned. We've got all the rest of August to work on it, the end of July, the rest of August to work on it here. Again, that'll be a large portion of your score for the final project. All right, awesome. So that's all I've got for you folks tonight. Did I commit for 2151? I'm not sure if I did or not. I don't think I did. Nope. Exceptions and file IO and midterm review. Look at that. Forgot. For the final project, right? No, I'm still finalizing exactly what that's going to be. I got an idea, but I have to finalize all the fine details of the different data structures you need to use for things. All right, awesome. Let me put on my ending screen here. We'll go send a raid off somewhere else. We got the rest of the night. If you got questions or concerns, let me know. I'll be around to answer them. We do have office hours tonight, 10 to 11. And then next week, I won't be live, right? That's reserved totally for the midterm. Again, there's a 4-hour time limit, so start it anytime you want in that 24-hour period. And just make sure you hit submit within 4 hours and it'll be fine. All right, why don't we go check out Rob, see what he's doing. Rob. Looks like he's doing his boost class again. He's a real nice guy. Knows all sorts of cool tech things. We'll head over that way, say hi, learn some things. You folks take care. Let me know what I can do to help. All right, take care, everybody.